So constraint optimization or constraint minimization problems. In order to talk about this, we kind of have to remind ourselves of how to deal with minimization problems in general. And that's what I'll do in this video. I'll focus on a very classical example, right? How do we obtain a weak formulation for a standard linear elasticity problem from the minimization of an energy potential. And the second thing that I'd like to point out in this video is that theory, that weak formulation, becomes problematic in the incompressible regime, or the incompressible limit. So, and the incompressible and so you might have heard that incompressible solids are quite difficult to treat, but maybe you don't quite know why that is. And again, here we have partly physics, partly math, and partly numerics. So I'll try to point that out in this lecture. So minimization problems. How do you obtain a weak statement for the linear elasticity problems from the perspective of a minimization problem? Well, we have to define an energy potential. And of course, the energy potential that we're typically dealing with is the strain energy. So linear elasticity. So we obtain it over, we define an energy potential. There we go. As some functional E. Well, what was a functional again? That goes back all the way to the earlier videos here. A functional was some operation that takes a function and produces a number, a scalar. Yeah, so we have here the energy functional in the sense that we give it a function, and in this case it's a vector valued function, and it performs a computation and gives us a scalar number, which is then the energy. That's the energy functional. And the operation that we perform here is that we obtain the internal energy as half of the strain of that field V, double contracted with the stress of that field V. And then we have some external loading as well, one of which is a body force, and one of which is an externally applied traction on a subset of our domain here, partial omega n. And so given any vector valued function, I can obtain what the energy would be according to this energy potential. So let me define some notation here. We're dealing with small strains here, so epsilon of some function v is going to be equal to half of the symmetric gradient, which is equal to the gradient of v plus this transpose gradient of v. And the stress as a function of some vector valued function. So this is second order tensor, this is also a second order tensor. Specify that here. In general, we would write that as the elasticity, fourth order elasticity tensor, which is a material tensor, material parameter, double contracted with the strain. And then in linear elasticity, we can actually show that there's just a very finite number of ways that we can represent that double contraction. And the one that I think is particularly insightful from the perspective of moving towards an incompressible solid is that sigma of v is going to be equal to, well, that's the one on the left already. It's going to be equal to minus lambda times the trace of epsilon. Yeah. Let me find my original statement. I also don't know these things by heart. Sorry. So it's 2 times mu times epsilon of v plus lambda times the trace of epsilon times the identity tension. Yeah, and these are Leibniz first and second parameters. So this is Leibniz first, lambda is Leibniz first, and second parameters. Okay. No. Yeah, okay. Think for a second if I already want to motivate what happens in the case of an incompressible solid, but I think we'll get to that towards the end. Okay, so how do the equations of linear elasticity now follow from this energy potential? Well, what we're going to do is we're going to define our solution U. So this energy potential, we can obtain energy for any possible vector valued function. So now we're going to define our solution U as the solution. So U is equal to the solution that minimizes the energy potential for all possible functions that are permissible. Yeah, and since we're dealing with first derivatives here, that means that we are looking at functions h1, well, they're vector valued, so h1d, and then I'll somehow also specify boundary conditions in the sense that on all domains that are not partial omega n here, we have Dirichlet conditions, and that's where we specify 0 values. Okay, so I'm not quite done yet. So what does it say right now? We have the infimum of our energy potential of sampled over a whole bunch of different functions, and then we'll take the minimum over all these functions. But the minimum of a bunch of scalars is still a scalar, and the left-hand side equation is a vector. So I'm going to introduce a little bit of notation here, and that is this new funny operator called arginf. And that is the operation that takes the argument of the thing that produces the infimum. Yeah. So what that means is that we have a certain function v that produces this infimum, the minimum of all the potential energies. And that function, so the argument of that minimization, that function v, that is the output of arginf, and that's going to be equal to our solution. Yeah. So we're defining our solution as the function that minimizes this energy potential. So how do I deal with that? So minimization, and I'm actually not sure to what extent this is going to be a repeat for some of you. I'm just going to move forward and hope that it's not going to be too boring. So clearly, if we're normally dealing with minima in standard calculus of an arbitrary function, then we say that the minimum occurs at a point where the derivative is equal to 0, right? So if this function, we call this f of x, then so f in x, then that point is the point that corresponds to the infimum of x, or sorry, the infimum of f of x for all possible x, or x in, let's call this, that's what we call our domain D. So for all function or all values x in that domain, in the domain of our function that I've drawn here, we're obtaining the minimal value, so that's the infimum of fx. So now this x here, this x is actually the argument of the infimum of f of x for all x in the domain. And at that point, we know that x is such that the first derivative of f is 0. Right? So we're trying to do now something similar here, but rather than a function that takes a scalar value and produces a scalar, we now have a functional that takes a function and produces a scalar. So how do we perform an operation that is similar to the one here on the right? Well, in order to do that, we kind of have to think about what this was exactly, right? We're so familiar with taking derivatives that sometimes we kind of forget what this operation really is. So the definition of derivative in this sense is that we take the limit of fx plus some change dx then we subtract the original value f of x and we divide by dx, and then we take the limit from dx goes to 0. And that's what we define to be the derivative at that point. So let's try and do something similar here on the left. Yeah, so what would that mean? That would be the limit of our strain energy E, well, at our solution U, right? Just like this is going to be at x. You know what, I don't like the dx here. Even though that's very customary, I'm going to do this slightly different because I feel like it might be confusing that there's an x in dx. So I'm just going to say plus delta. Delta. Because in the end, it's just a little number, right? We're increasing x with just a little number. And then that number is going to go to 0. So here we should do something similar. So somehow I'm going to increase u with something. Then I'm going to subtract my energy at the point again, u, and then I'm going to divide by somehow that thing that I'm adding here. So how am I going to do this? The thing that E takes as an input argument is a function. So somehow whatever is in here has to be a function. So I'll use v. Right? I can only increment a function by a function. I can only add two functions together. Clearly I can add a value to a function, but in that sense, this value is itself also a function. But now I can't really take the limit of a function going to 0. So what I can do instead is I can multiply this function by a scalar number. Let's use this epsilon. So just to be clear, this is now an epsilon. This is not the same symbol as this guy. That's not the same. The upper symbol is the symbol that means in. And now I'm talking about an epsilon. And now I can divide by that number, epsilon. And now I can take the limit of epsilon going to 0. And so this is sort of the equivalent of what we have on the left here. And so what we have on the right here. On the right we have that we take a function at a certain location, then we move away from that location a little bit and we see if we get an increase or not. And if not, then we're at a valley. And that's what we have on the left here as well, but rather than sampling at a point, we're sampling at a function, namely a function u, and we're trying to move away from our solution function a little bit by another function, epsilon times v, and then in every possible direction v, so this has to now be true for all v, that incremental change, right, the limit where epsilon goes to 0, has to vanish, and then we're also in a valley, a minimal. So if we find some position where this is true, then we have found our solution u that minimizes that satisfies this statement here. It's the argument that minimizes our energy potential. So this is what we call. There's different names for this. We can call this the directional derivative. Sometimes we call it that because we're taking the derivative of E in the direction of this function v. Other names for these are the Gateau derivative or the functional derivative. And I think the functional derivative kind of fits the bill best because we're taking the derivative of a functional. I also think that functional derivative is something that sort of is slightly more general than just the Gateau derivative. I think formally this might be specifically the Gateau derivative, although I'm not 100% sure. So we often also see this written in a slightly different form, and I think I should motivate that as well. That at the point u, so we're searching for u such that the derivative with respect to epsilon of e u plus epsilon v at the point where epsilon is equal to 0 is going to be equal to 0. I'm writing it correctly. So does this make sense? How does the second statement follow from the first? Well, in order to make the same connection, let me also motivate that on the right here. What I could also do is I could rewrite this a little bit. I could say, well, I'm going to take f at x plus plus delta, and I'm going to take d delta now at the point where delta is equal to 0. So that's kind of the same thing as what we have here on the left now. So does that make sense? Let's try to again think about what is the derivative. Well, that was this limiting statement here. So this again is now the limit of I don't want to call this delta. Running out of symbols here. No, I will call it delta. The limit of now, let's call this d, goes to 0 of, well, we have, let's just put down the same statement, right? We have f x plus delta, but now plus d, minus f x plus delta, divided by d, but now specifically evaluated at delta is equal to 0, which means that effectively this is the same thing as doing this, which is clearly the same thing as doing that. Yeah? So the thing that I'm trying to motivate is why is this statement, or sorry, this complete statement similar to this statement? Well, that's the same way that this statement is clearly the same as this statement, and hence the same as this statement. Yeah? Now, I don't know exactly which statement I prefer. These ones I think are similarly easy or similarly straightforward to work with, but you could work with either one. So maybe you're most familiar with working with the lower one, but I think that one is actually the least intuitive one based on what I just said. I could motivate this equation directly from original minimization point, whereas the lower one we had to think about why is exactly why is there this equivalence. So you know what, for this video I'll actually use this statement to obtain our weak formulation. Although it's going to be the same thing as using the lower one. Okay, so what I'm going to do is I'm just going to substitute these input arguments into my definition of my energy. And I'll do that with u plus epsilon v, and I'll do that just with u. I'm going to subtract that, and I'm going to divide by epsilon, and then we're going to take the limit. Yeah, so I'm just going to exactly perform what I've written down right here. So okay. So what is the strain of u plus epsilon v? That's going to be the strain of, or what did I say? I said I should say, what is the energy of u plus epsilon v? That's going to be the integral over the domain of the strain of u plus epsilon v. Before I have to write 20 lines, what I'll do is I'll already realize right now, well, my strain operator is a linear operator, which means that I'll be allowed to simply separate this out. So I actually get epsilon of u plus epsilon of the strain of v. Double contracted by c, double contracted by, again, the same thing. And there should be a half up front here. Now then I had some more terms. I had minus f dotted with u plus epsilon v. And I had minus integral on the Neumann boundary of the traction, also dotted with u plus epsilon v. So how does this work out? Well, these are just all linear operations. I can expand this. So I get half of epsilon u c epsilon u. Similarly, I get half of epsilon strain of v, c strain of epsilon strain of v. So that gives me half times epsilon squared times the strain of v, c strain of v. And then plus half of epsilon times the strain of v, double contracted with c times the strain of u. And then I would also get the same thing again, but now with u and v flipped. However, because we have these symmetries in the strain operator is a symmetric operator, and also due to thermodynamic considerations, also this elasticity tensor C, this material tensor, also has certain symmetries inside of it, such that we can actually flip these and get the same expression, the same value, which means that I can simply add these together, and 2 times a half is going to give me just that. Okay, so now I have this one. Maybe I can copy these guys again as well. Yeah, so I have these two expressions. So they're the same thing. What was that? Well, that was the one on the left here. Yeah. So now we're going to subtract E of U, the energy of my solution U. Well, what's that? Well, that's precisely this term and precisely F dot U and also T dot U. Right? So we're left with just these leftover terms. The next operation I'll do is I'm going to divide by. Did this somehow just change color? Interesting. Huh. Okay, so the next thing I'll do is I'll divide by epsilon. Now if I divide by epsilon, then the square drops out. Here we have a division by epsilon, that goes away. And here we still have these guys, they also go away. And after that, I'm going to take the limit of epsilon goes to 0. Yeah, that means that we still have one epsilon multiplication left here, so this one also drops out altogether. Yeah, so then in summary, if we take the limit of epsilon goes to 0, sorry, this symbol, of E of U plus epsilon v minus e of u divided by epsilon. That's going to be equal to all my leftover terms here. That's this one and these ones. So that's going to be equal to the integral of the domain of epsilon v double contracted with c double contracted with epsilon of u minus f dot v minus t dot v. Okay, and our statement was that my solution u will be such that this has to be true for all directions of our small fluctuation v. Yeah? So here we precisely have our very classical weak statement, and sorry, this has to be equal to 0, of course. This has to be equal to 0 for all functions v. And here we have our very classical weak formulation of the linear elasticity equations. Okay, so this was a bit of a rehearsal of how to deal with minimization, minimization of potentials to obtain weak formulations. But I also said that I wanted to point out why this becomes difficult in the incompressible limit. Now, to do this, we have to expand this, this term that is still a little obscure right here. Okay, so we have C double contracted with epsilon of u. That was our stress, and we had an expression for that. That is 2 times mu times the strain plus lambda times the trace of epsilon. Yeah, so I'll substitute that. So before I do that, actually, we let me point out this is of the form find a solution u in our potential function space, or functions in the space of functions that we're committing these operations on, such that b u comma v is going to be equal to L of v for all v in that same space. Yeah, and L of v is of course the ones that we have right here, but move to the right hand side. And this one is going to be our bilinear form. Okay, so now let me substitute our definition of our stress with the Lamé parameters. So we have our strain of V double contracted with, and now we have this expression, double contracted with 2 times mu times that. So maybe I should write this like this. Plus lambda epsilon v times the trace, double contracted with I times the trace of u, trace of the great strain of u, probably. Check that. Yes. Okay. Now there's a couple of interesting things that we can still manipulate this. First of all, let me talk about this double contraction. So what was this double contraction? Is in tensor notation that if we were to represent our tensors by matrices, then we're essentially multiplying each index of the matrix, right? So given that in matrix notation I can be written as 1, 0, 0, 0, 1. That means that a double contraction of the strain with I is going to be of the form, is simply going to be the sum of the diagonal components of the strain tensor. We're taking the double contraction, the sum of all these, the multiplication with every component. Only the components along the diagonal are non-zero, which means that we get here the sum of 1 times the strain 1, 1, 1 times strain 2, 2, and 1 times strain 3, 3. So that is actually precisely equal to the trace of epsilon v. Yeah, so that's why this is a symmetric bilinear form. Yeah, so this is equal to the trace. And the trace was the sum of the diagonals. Now there's another interesting interpretation though. If we take a look at what is actually on these diagonals, then we find that, well, what was the definition of our strain of a vector field is going to be equal to half of the gradient of that field plus the transpose gradient of that field. So epsilon v ij is going to be equal to half of partial vi partial xj plus partial vj partial xi, which means that epsilon vii is going to be equal to half of simply, well, the same thing twice, so that's going to kill the half, is simply equal to partial vi partial xi. And if I now sum over all these indices, then we get that precisely the trace again, the trace of epsilon v is going to be equal to the sum of these partial derivatives, and that is exactly the definition of the divergence. Yeah? So another interpretation, or another way of writing now the bilinear form, b u comma v is going to be equal as the integral of 2 times mu times the gradient. Well, let me stay with that. Plus lambda times the divergence of v times the divergence of u. Okay, so now again let's try and answer the question. What happens if we go to the incompressible limit? Well, what we know in the incompressible limit is if the material parameters are such that our Poisson ratio is going to be equal to half. Yeah, that's how we characterize an incompressible material. Example often being rubber. And the definition of the Poisson ratio in terms of mu and lambda is that mu can be written as actually half times lambda divided by lambda plus mu. So we see that if when lambda divided by mu goes to infinity, what happens then? Well, let me rewrite this. Let me divide up above and below the fraction by lambda, gives me 1 over 1 plus mu divided by lambda. So that means similarly that, or why, I don't know why I'm writing it like that. I'm gonna go with mu divided by lambda goes to 0. Yeah, so if that happens, then we see that that limits to half. So in this case, we have an incompressible solid. So what happens to our bilinear form if we have an incompressible solid? Let me divide the entire weak statement by lambda. So I'm gonna divide both sides of the equation by lambda. So I'll divide left hand side and right hand side by lambda. Then, remember that we did something similar for the advection problem where we're dividing by the maximum value of the advective field. So it gives us sort of a normalized bilinear form as 2 times mu divided by lambda plus the divergence of v times the divergence of u. So how do we know if a problem like this is stable or not, and if it has a unique solution or not? Well, that's exactly the theory that we developed earlier. And one of the key characteristics, or one of the key concepts in that theory was the coercivity constant involved in a bilinear form like this. So what we want is that we have b, u of v, is going to be larger than or equal to the norm. If I substitute the same function in both slots, right? It's going to be equal to larger than or equal to the norm of v squared in the relevant norm times c, where c is larger than 0, and that has to be true for all these functions. So let's take a look at the above statement here. What happens if mu divided by lambda is going to go to 0? So in the limit of then we have b, v, comma v is going to be larger than or equal to, well, just the integral of the divergence of these functions square. Right, this is the only leftover term. This one is going to be 0. That's the only leftover term. So is that a coercivity statement? Well, it's going to be larger than 0, larger than or equal to 0. But I can choose functions. So choose any function that is divergence free, and that then gives me b tilde v comma v is equal to 0. Yeah, so that means that the coercivity constant also limits to 0 as mu over lambda goes to 0, right? So in that sense, it's really this first term here that that gives us the coercivity of the bilinear form. You have sort of similar inequalities as Poincaré's inequality, the one that we ended up using for the advection diffusion equation. For these vector fields, they're called Korn's inequalities. They're a little bit more tricky. But in the limit of mu divided by lambda going to 0, this whole term drops out. So the thing that gives us the coercivity of our linear elasticity equations actually starts to vanish. So does that mean that we cannot obtain a solution? Well, no, it does not mean that we cannot obtain a solution. A couple of reasons for those were, first of all, we're taking a limit here, right? We're never actually substituting that expression. So we always have a non-zero expression up front here, but it becomes very, very, very small. That means that our coercivity constant becomes very, very, very small. Now, for any non-zero coercivity constant, we do obtain a unique solution. So we have existence and we have uniqueness. However, a very small coercivity constant meant that we have a highly unstable partial differential equation. And what that means is that if we have a slight change of data, in the sense of a slight change of body forces, of tractions, and specifically of Dirichlet conditions, that we get wildly different solutions. And in general, our sensitive partial differential equation means that, or an unstable partial differential equation means that it's very sensitive to perturbations, to small mistakes, to change of data. And if we use a numerical method to treat or to approximate a solution to the partial differential equation, then we will make an error, right? That's just the nature of numerical methods. And the error that we're making is going to spoil the results for a very unstable partial differential equation. The error is going to affect the solution itself. There's going to be sort of a feedback in that sense. And that's the same sort of feedback that we also get for unstable partial differential equations for advection-based problems. Yeah? It's not the fact that the finite element method is not able to approximate the solution. It's just that the partial differential equation in the weak statement is so sensitive to anything, including the error, that you just get very bad approximations. Even in the limiting case of mu goes to mu over lambda is exactly 0. Yeah, I would have to look into if that still permits a solution or not. Clearly, we don't have a coercive problem anymore, because at that point the coercivity constant is precisely equal to 0. But we said before that is not necessarily a complete problem. We would simply have to resolve to the subconditions. But in general, you don't want to use this formulation for those limiting cases, or also values that are strongly neighboring those limiting cases, because we get such a sensitive partial differential equation, and it's going to be very sensitive to errors that we're making in a numerical method. So I think that's where I'll stop for this video. I think I've talked for over 40 minutes, so that should be enough. So what we did so far is we addressed that problem. We pointed out a problem. Well, first of all, we rehearsed a bit of theory. We rehearsed how you take minimizations, how you do minimization of potentials, of functional minimization. And secondly, we then saw that actually for quite a relevant problem, a linear elasticity, if we get certain material parameter choices, namely limiting towards an incompressible material, that we get problems. And that kind of gets us back to our original list of motivation for mixed formulations. And that is that we get a certain constraint, namely the incompressibility constraint, that we want to enforce in a minimization problem. And essentially that means that we can write these equations in a different form that does no longer have a vanishing coercivity constant, yeah, and that ends up being a saddle point problem. And for those, we have a new space, which will be the pressure space, or a new solution function, which is a pressure solution. So that makes that a mixed formulation then. So the point is that we find now a formulation that is unsuitable for numerical treatment because it will give unstable results. So we're going to change our formulation, and that's what we'll do in the next video. So thank you for your attention.